Take a look around you. So many of the products that we take for granted today, from kettles and light switches to mobile phones and tablets, are made from a variety of metals and plastics. But who were the people who discovered the properties of these substances and how to manipulate them to create things that are still relevant to us in the 21st century? And what role did Hinxton play in these discoveries? The story begins shortly after the Second World War, when a fashion for the commercial and industrial sector to support basic academic research began to emerge and help aid Britain's post-war recovery. The engineering group Tube Investments was part of this trend, largely due to the influence of Sir Ben Lockspicer, the Director General of Scientific Research in the wartime Ministry of Aircraft Production, and later, the first president of CERN. Tube Investments wanted to create a laboratory to undertake the study of materials and their properties. The task of setting it up was given to Dr. Philip Bowden. The Hinxton Hall estate fulfilled two key criteria. It was close enough to the University of Cambridge to enable collaborative research, but far enough away from the manufacturing operations of Tube Investments to avoid the laboratory being distracted by production problems. Tube Investments bought the site in 1953, and in 1954 the first scientists moved in. Apart from urgent alterations to the old hall, one of the first actions was to roof in the stable yard and fill it with the best machine tools money could buy, in the belief that the hub of any laboratory should be a first-class workshop.
Just after the war, nearly all the big companies all bought up old houses like the Welding Institute not far away, Babraham. All of these places were all bought up on the cheap, I think, really. And everybody, all the major companies thought they should have research facilities.
In contrast to Tube Investments' commercial activity, the research laboratory initially commenced blue skies research into the physical properties of irradiated plastics and metals. The latest Siemens electron microscope was installed in the butler's pantry of the old hall, where the thicker walls, originally intended to protect the family silver, were found to bring about the lowest ambient magnetic field on the site, and hence the best operating conditions for the microscope. In the following year, Jim Mentor, one of Bowden's research students and among the first scientists to join the laboratory, used it to achieve the first ever direct imaging of layers of atoms.
Jim Mentor, who for the first time was able to photograph planes of atoms in a crystal with the latest electron microscope. This caused quite a sensation, and I arrived at the laboratory. In the backwash of that, it was a global excitement.
A visiting American, armed with an air pollution sample taken from the top of one of the highest buildings in Chicago, was sufficiently impressed to remark that it was strange to sit in the butler's pantry of an English country house and find out which way the wind had been blowing last Thursday in Chicago. In 1957, Peter Duncombe, a physicist in the Cavendish Laboratory at the University of Cambridge, had developed the technique of scanning electron probe microanalysis. David Melford, a metallurgist newly arrived at Hinxton, thought this would be ideal for him to investigate a problem arising at the surface of steel during tube making.
Then when I met Peter and found out what his developments in the Cavendish Laboratory could do for metallurgists, that was tremendously exciting. I think the first night I saw it, I described it as God's gift to metallurgists, and we just had to have one, or I couldn't get on with my project.
Together, they designed the first such instrument for metallurgic use, which was then constructed in the Hinxton workshop. It attracted major outside interest, and within 4 months of its commissioning at the end of 1958, it was licensed to the Cambridge Instrument Company to produce commercially under the name Microscan.
Built on the optical microscope, where for a long time metallurgists could see what was there, and they would polish their samples and see the different constituents, but they didn't necessarily know what they were. So the advantage of the microanalyzer was to be able to pinpoint each one in turn and see what elements were there, and also to scan the beam across the sample and show what the distribution was of those elements.
Overcrowding of staff in the old hall became an increasing problem, so a brand new laboratory building adjacent to the hall was completed in 1958. The lab building is commemorated with a permanent installation that demarcates the original building footprint and can be viewed on the campus today. More breakthroughs arose when Peter Duncan joined the laboratory in 1959 and combined the technique of X-ray microanalysis with electron microscopy, thereby enabling the identification of particles less than 1,000th of a millimetre in diameter. His instrument EMMA, a combined electron microscope and microanalyzer, was also constructed in the Hinxton workshop. The successes of Mentor's group were well illustrated in Walter J. Moore's review of the proceedings of the 1959 Lake George Conference on the structure of properties of thin films. Maybe future scientific historians will ponder how and why, at mid-20th century, an English bicycle maker was contributing more than the entire US steel industry to basic research on metals. Bowden and his team had turned an empty country house into a first-class research laboratory, complete with an international reputation in no more than 5 years, respected by universities and taken very seriously by other major industrial laboratories.
It was for the first time that you could feel you were part of something instead of an infinitesimal cog in some huge organisation.
The 1960s saw a change in direction for the research laboratory as its outputs became more aligned to Tube Investments' commercial activities.
Some of the things we worked on were certainly from rally bicycles to Creeder kettles, Russell Hobbs. So you never knew what was coming through the door, really.
The world's first commercial superplastic aluminium alloy was developed, along with the forming press, which enabled sheets produced by British Aluminium to be moulded to shape, much like plastic, albeit at higher temperatures. A new company was formed to exploit this, TI Superform at Worcester, and one of the first applications was for the headbox of the Martin Baker ejector seat for jet aircraft. Another new company was set up, TI Trueform, to exploit an entirely novel rolling process, which could make ring components for jet engines of unprecedented width and dimensional accuracy. These companies exist to the present day. Through the 1970s and 80s, the laboratory supported the development of computer-aided design instrumentation and novel forms of ultrasonic testing for assimilation by the manufacturing companies. Among other research, new ways of magnetic stirring for molten steel and new vitreous enamels for home appliances also emerged. In 1959, the total staff numbered 130, and in 1979, near its zenith, there were 184 staff, of whom about 50 were graduates. The laboratory was a powerhouse of world-class technicians and apprentices, ahead of its time in many ways, and some of these were later sponsored to go to university, and even to take PhDs. An excellent canteen for communal lunches, staffed mainly by women from the neighbouring Hinxton village, also provided space for social gatherings. The laboratory closed in 1988. In a very real sense, it was the founding member of what would later become known as the Cambridge phenomenon, the fruitful interaction between university and industry.
This was an organisation that was really making a difference. And indeed it was. The frontiers of knowledge had been pushed back by this relatively small group of people. And it was the size of Hinxton which played a big role.
The scientific story doesn't end there. In 1992, it became the Sanger Centre, the home of the first Human Genome Project. Throughout the 34 years of its existence, Tube Investments produced a stream of technological innovations, but perhaps its greatest achievement is that it's remembered as a very happy place in which to have worked.